Evaluate the model on this instruction. Role-playing. One of the most common types of real-world instructions is role-playing, asking the model to assume a fictional character or a persona. Role-playing can serve two purposes. 1. Role-playing a character for users to interact with, usually for entertainment, such as in gaming or interactive storytelling. 2. Role-playing is a prompt engineering technique to improve the quality of a model's outputs, as discussed in Chapter 5 Evaluation Criteria 175. 8. The knowledge part is tricky, as the role-playing model shouldn't say things that Jackie Chan doesn't know. For example, if Jackie Chan doesn't speak Vietnamese, you should check that the role-playing model doesn't speak Vietnamese. The negative knowledge check is very important for gaming. You don't want an NPC to accidentally give players spoilers. For either purpose, role-playing is very common. LMSYS's analysis of 1 million conversations from their Vicuna demo and chatbot arena, Jing et al., 2023, shows that role-playing is their 8th most common use case, as shown in Figure 4.4. Role-playing is especially important for AI-powered NPCs, non-playable characters, in gaming, AI companions, and writing assistants. Figure 4.4. Top 10 most common instruction types in LMSYS's 1 million conversations dataset. Role-playing capability evaluation is hard to automate. Benchmarks to evaluate role-playing capability include RoleLLM, Wang et al., 2023, and Character Eval, Tu et al., 2024. Character Eval used human annotators and trained a reward model to evaluate each role-playing aspect on a 5-point scale. RoleLLM evaluates a model's ability to emulate a persona using both carefully crafted similarity scores, how similar the generated outputs are to the expected outputs, and AI judges. If AI in your application is supposed to assume a certain role, make sure to evaluate whether your model stays in character. Depending on the role, you might be able to create heuristics to evaluate the model's outputs. For example, if the role is someone who doesn't talk a lot, a heuristic would be the average of the model's outputs. Other than that, the easiest automatic evaluation approach is AI as a judge. You should evaluate the role-playing AI on both style and knowledge. For example, if a model is supposed to talk like Jackie Chan, its outputs should capture Jackie Chan's style and are generated based on Jackie Chan's knowledge. 8 AI judges for different roles will need different prompts. To give you a sense of what an AI judge's prompt looks like, here is the beginning of the prompt used by the 176, Chapter 4, Evaluate AI Systems. RoleLLM AI judge to rank models based on their ability to play a certain role. For the full prompt, please check out Wang et al. 2023. System instruction: you are a role-playing performance comparison assistant. You should rank the models based on the role characteristics and text quality of their responses. The rankings are then output using Python dictionaries and lists. User prompt: the models below are to play the role of role_name. The role description of role_name is role_description_and_catch for SES. I need to rank the following models based on the two criteria below. 1. Which one has more pronounced role speaking style, and speaks more in line with the role description? The more distinctive the speaking style, the better. 2. Which one's output contains more knowledge and memories related to the role, the richer, the better. If the question contains reference answers, then the role minus specific knowledge and memories are based on the reference answer. Cost and latency: a model that generates high-quality outputs but is too slow and expensive to run will not be useful. When evaluating models, it's important to balance model quality, latency, and cost. Many companies opt for lower-quality models if they provide better cost and latency. Cost and latency optimization are discussed in detail in Chapter 9, so this section will be quick. Optimizing for multiple objectives is an active field of study called Pareto optimization. When optimizing for multiple objectives, it's important to be clear about what objectives you can and can't compromise on. For example, if latency is something you can't compromise on, you start with latency expectations for different models, filter out all the models that don't meet your latency requirements, and then pick the best among the rest. There are multiple metrics for latency for foundation models, including but not limited to time to first token, time per token, time between tokens, time per query, etc. It's important to understand what latency metrics matter to you. Latency depends not only on the underlying model but also on each prompt and sampling variables. Autoregressive language models typically generate outputs token by token. The more tokens it has to generate, the higher the total latency. You can control the total latency observed by users by careful prompting, such as instructing evaluation criteria 177. 9. However, the electricity cost might be different, depending on the usage. The model to be concise, setting a stopping condition for generation, discussed in Chapter 2, or other optimization techniques, discussed in Chapter 9. When evaluating models based on latency, it's important to differentiate between the must-have and the nice-to-have. If you ask users if they want lower latency, nobody will ever say no. But high latency is often an annoyance, not a deal breaker. If you use model APIs, they typically charge by tokens. The more input and output tokens you use, the more expensive it is. Many applications then try to reduce the input and output token count to manage cost. If you host your own models, your cost, outside engineering cost, is compute. To make the most out of the machines they have, many people choose the largest models that can fit their machines. For example, GPUs usually come with 16 GB, 24 GB, 48 GB, and 80 GB of memory. Therefore, many popular models are those that max out these memory configurations. It's not a coincidence that many models today have 7 billion or 65 billion parameters. If you use model APIs, your cost per token usually doesn't change much as you scale. However, if you host your own models, your cost per token can get much cheaper as you scale. If you've already invested in a cluster that can serve a maximum of 1 billion tokens a day, the compute cost remains the same whether you serve 1 million tokens or 1 billion tokens a day. 9. Therefore, at different scales, companies need to re-evaluate whether it makes more sense to use model APIs or to host their own models. Table 4.3 shows criteria you might use to evaluate models for your application. The row scale is especially important when evaluating model APIs, because you need a model API service that can support your scale. Table 4.3. An example of criteria used to select models for a fictional application. Criteria metric benchmark hard requirement ideal cost per output token X less than $30. 00/1M tokens less than $15. 00/1M token scale TPM, tokens per minute, X greater than 1M TPM 1M TPM latency time to first token, P90, internal user prompt dataset less than 200 milliseconds less than 100 milliseconds latency time per total query, P90. Internal user prompt dataset 1M30s overall model quality ELO score chatbot arenas ranking greater than 1200 greater than 1250 178, Chapter 4, Evaluate AI Systems. Criteria metric benchmark hard requirement ideal code generation capability pass at 1 human eval greater than 90% greater than 95% factual consistency internal GPT metric internal hallucination dataset 0. 8 greater than 0. 9. Now that you have your criteria, let's move on to the next step and use them to select the best model for your application. Model selection. At the end of the day, you don't really care about which model is the best. You care about which model is the best for your applications. Once you've defined the criteria for your application, you should evaluate models against these criteria. During the application development process, as you progress through different adaptation techniques, you'll have to do model selection over and over again. For example, prompt engineering might start with the strongest model overall to evaluate feasibility and then work backward to see if smaller models would work. If you decide to do fine-tuning, you might start with a small model to test your code and move toward the biggest model that fits your hardware constraints, e.g., 1 GPU. In general, the selection process for each technique typically involves 2 steps. 1. Figuring out the best achievable performance. 2. Mapping models along the cost-performance axis and choosing the model that gives the best performance for your bucks. However, the actual selection process is a lot more nuanced. Let's explore what it looks like. Model selection workflow. When looking at models, it's important to differentiate between hard attributes, what is impossible or impractical for you to change, and soft attributes, what you can and are willing to change. Hard attributes are often the results of decisions made by model providers, licenses, training data, model size, or your own policies, privacy, control. For some use cases, the hard attributes can reduce the pool of potential models significantly. Soft attributes are attributes that can be improved upon, such as accuracy, toxicity, or factual consistency. When estimating how much you can improve on a certain attribute, it can be tricky to balance being optimistic and being realistic. I've had situations where a model's accuracy hovered around 20% for the first few prompts. Model selection 179. However, the accuracy jumped to 70% after I decomposed the task into 2 steps. At the same time, I've had situations where a model remained unusable for my task even after weeks of tweaking, and I had to give up on that model. What you define as hard and soft attributes depends on both the model and your use case. For example, latency is a soft attribute if you have access to the model to optimize it to run faster. It's a hard attribute if you use a model hosted by someone else. At a high level, the evaluation workflow consists of 4 steps, see Figure 4.5.1. Filter out models whose hard attributes don't work for you. Your list of hard attributes depends heavily on your own internal policies, whether you want to use commercial APIs or host your own models. 2. Use publicly available information, e.g., benchmark performance and leaderboard ranking, to narrow down the most promising models to experiment with, balancing different objectives such as model quality, latency, and cost. 3. Run experiments with your own evaluation pipeline to find the best model, again, balancing all your objectives. 4. Continually monitor your model in production to detect failure and collect feedback to improve your application. Figure 4.5. An overview of the evaluation workflow to evaluate models for your application. 180. Chapter 4. Evaluate AI systems. 10. Another argument for making training data public is that since models are likely trained on data scraped from the internet, which was generated by the public should have the right to access the model's training data. These 4 steps are iterative. You might want to change the decision from a previous step with newer information from the current step. For example, you might entirely want to host open source models. However, after public and private evaluation, you might realize that open source models can't achieve the level of performance you want and have to switch to commercial APIs. Chapter 10 discusses monitoring and collecting user feedback. The rest of this chapter will discuss the first 3 steps. First, let's discuss a question that most teams will visit more than once: to use model APIs or to host models themselves. We'll then continue to how to navigate the dizzying number of public benchmarks and why you can't trust them. This will set the stage for the last section in the chapter. Because public benchmarks can't be trusted, you need to design your own evaluation pipeline with prompts and metrics you can trust. Model build versus buy. An evergreen question for companies when leveraging any technology is whether to build or buy. Since most companies won't be building foundation models from scratch, the question is whether to use commercial model APIs or host an open source model yourself. The answer to this question can significantly reduce your candidate model pool. Let's first go into what exactly open source means when it comes to models, then discuss the pros and cons of these 2 approaches. Open source, open weight, and model licenses. The term open source model has become contentious. Originally, open source was used to refer to any model that people can download and use. For many use cases, being able to download the model is sufficient. However, some people argue that since a model's performance is largely a function of what data it was trained on, a model should be considered open only if its training data is also made publicly available. Open data allows more flexible model usage, such as retraining the model from scratch with modifications in the model architecture, training process, or the training data itself. Open data also makes it easier to understand the model. Some use cases also required access to the training data for auditing purposes, for example, to make sure that the model wasn't trained on compromised or illegally acquired data. 10 Model Selection 181. 11 In spirit, this restriction is similar to the Elastic license that forbids companies from offering the open-source version of Elastic as a hosted service and competing with the Elasticsearch platform. To signal whether the data is also open, the term open weight is used for models that don't come with open data, whereas the term open model is used for models that come with open data. Some people argue that the term open source should be reserved only for fully open models. In this book, for simplicity, I use open source to refer to all models whose weights are made public, regardless of their training data's availability and licenses. As of this writing, the vast majority of open source models are open weight only. Model developers might hide training data information on purpose, as this informa tie-in can open model developers to public scrutiny and potential lawsuits. Another important attribute of open source models is their licenses. Before Foundation tie-in models, the open source world was confusing enough, with so many different licenses, such as MIT, Massachusetts Institute of Technology, Apache 2.0, GNU General Public License, GPL, BSD, Berkeley Software Distribution, Creative Commons, etc. Open source models made the licensing situation worse. Many models are released under their own unique licenses. For example, Meta released Llama 2 under the Llama 2 Community License Agreement and Llama 3 under the Llama 3 Community License Agreement. Hugging Face released their model BigCode under the BigCode Open Rail MV1 license. However, I hope that, over time, the community will converge towards some standard licenses. Both Google's Gemma and Mistral 7b were released under Apache 2.0. Each license has its own conditions, so it'll be up to you to evaluate each license for your needs. However, here are a few questions that I think everyone should ask. Does the license allow commercial use? When Meta's first Llama model was released, it was under a non-commercial license. If it allows commercial use, are there any restrictions? Llama 2 and Llama 3 specify that applications with more than 700 million monthly active users require a special license from Meta. 11 Does the license allow using the model's outputs to train or improve upon other models? Synthetic data, generated by existing models, is an important source of data to train future models, discussed together with other data synthesis topics in Chapter 8. A use case of data synthesis is model distillation, teaching a student, typically a much smaller model, to mimic the behavior of a teacher. 182, Chapter 4, Evaluate AI Systems. 12 It's possible that a model's output can't be used to improve other models, even if its license allows that. Consider Model X that is trained on ChatGPT's outputs. X might have a license that allows this, but if ChatGPT doesn't, then X violated ChatGPT's terms of use, and therefore, X can't be used. This is why knowing a model's data lineage is so important. Typically a much larger model. Mistral didn't allow this originally but later changed its license. As of this writing, the Llama licenses still don't allow it. 12 Some people use the term restricted weight to refer to open source models with restricted licenses. However, I find this term ambiguous, since all sensible licenses have restrictions, e.g., you shouldn't be able to use the model to commit genocide. Open source models versus model APIs. For a model to be accessible to users, a machine needs to host and run it. The service that hosts the model and receives user queries, runs the model to generate responses for queries, and returns these responses to the users is called an inference service. The interface users interact with is called the model API, as shown in Figure 4.6. The term model API is typically used to refer to the API of the inference service, but there are also APIs for other model services, such as fine-tuning APIs and evaluation APIs. Chapter 9 discusses how to optimize inference services. Figure 4.6. An inference service runs the model and provides an interface for users to access the model. After developing a developer can choose to open source it, make it accessible via an API, or both. Many model developers are also model service providers. Cohere and Mistral open source some models and provide APIs for some. OpenAI is typically known for their commercial models, but they've also open-sourced models, GPT-2, CLIP. Typically, model providers open-source weaker models and keep their best models behind paywalls, either via APIs or to power their products. Model APIs can be available through model providers, such as OpenAI and Anthropic, cloud service providers, such as Azure and GCP, Google Cloud Platform, or third-party API providers, such as Databricks Mosaic, Anyscale, etc. The same model can be available through different APIs with different features, constraints, and pricings. For example, GPT-4 is available through both OpenAI and Model Selection 183. 13 For example, as of this writing, you can access GPT-4 models only via OpenAI or Azure. Some might argue that being able to provide services on top of OpenAI's proprietary models is a key reason Microsoft invested in OpenAI. 14 Interestingly enough, some companies with strict data privacy requirements have told me that even though they can't usually send data to third-party services, they're okay with sending their data to models hosted on GCP, AWS, and Azure. For these companies, the data privacy policy is more about what services they can trust. They trust big cloud providers but don't trust other startups. 15 The story was reported by several outlets, including TechRadar. Samsung workers made a major error by using ChatGPT, by Lewis Madison, April 2023. Azure APIs. There might be slight differences in the performance of the same model provided through different APIs, as different APIs might use different techniques to optimize this model, so make sure to run thorough tests when you switch between model APIs. Commercial models are only accessible via APIs licensed by the model developers. 13 Open source models can be supported by any API provider, allowing you to pick and choose the provider that works best for you. For commercial model providers, models are their competitive advantages. For API providers that don't have their own models, APIs are their competitive advantages. This means API providers might be more motivated to provide better APIs with better pricing. Since building scalable inference services for larger models is non-trivial, many companies don't want to build them themselves. This has led to the creation of many third-party inference and fine-tuning services on top of open-source models. Major cloud providers like AWS, Azure, and GCP all provide API access to popular open-source models. A plethora of startups are doing the same. There are also commercial API providers that can deploy their services within your private networks. In this discussion, I treat these privately deployed commercial APIs similarly to self-hosted models. The answer to whether to host a model yourself or use a model API depends on the use case. And the same use case can change over time. Here are 7 axes to consider: data privacy, data lineage, performance, functionality, costs, control, and on-device deployment. Data privacy. Externally hosted model APIs are out of the question for companies with strict data privacy policies that can't send data outside of the organization. 14 One of the most notable early incidents was when Samsung employees put Samsung's proprietary information into ChatGPT, accidentally leaking the company's secrets. 15 It's unclear how Samsung discovered this leak and how the leaked information was 184, Chapter 4, Evaluate AI Systems. Used against Samsung. However, the incident was serious enough for Samsung to ban ChatGPT in May 2023. Some countries have laws that forbid sending certain data outside their borders. If a model API provider wants to serve these use cases, they will have to set up servers in these countries. If you use a model API, there's a risk that the API provider will use your data to train its models. Even though most model API providers claim they don't do that, their policies can change. In August 2023, Zoom faced a backlash after people found out the company had quietly changed its terms of service to let Zoom use user service-generated data, including product usage data and diagnostics data, to train its AI models. What's the problem with people using your data to train their models? While research in this area is still sparse, some studies suggest that AI models can memorize their training samples. For example, it's been found that Hugging Face's StarCoder model memorizes 8% of its training set. These memorized samples can be accidentally leaked to users or intentionally exploited by bad actors, as demonstrated in Chapter 5. Data lineage and copyright. Data lineage and copyright concerns can steer a company in many directions, toward open-source models, toward proprietary models, or away from both. For most models, there's little transparency about what data a model is trained on. In Gemini's technical report, Google went into detail about the model's performance but said nothing about the model's training data other than that all data enrichment workers are paid at least a local living wage. OpenAI's CTO wasn't able to provide a satisfactory answer when asked what data was used to train their models. On top of that, the IP laws around AI are actively evolving. While the U.S. Patent and Trademark Office, USPTO, made clear in 2024 that AI-assisted inventions are not categorically unpatentable, an AI application's patentability depends on whether the human contribution to an innovation is significant enough to qualify for a patent. It's also unclear whether, if a model was trained on copyrighted data, and you use this model to create your product, you can defend your product's IP. Many companies whose existence depends upon their IPs, such as gaming and movie studios, are hesitant to use AI to aid in the creation of their products, at least until IP laws around AI are clarified. James Vincent, The Verge, November 15, 2022. Concerns over data lineage have driven some companies toward fully open models, whose training data has been made publicly available. The argument is that this allows the community to inspect the data and make sure that it's safe to use. Wallet Model Selection 185. 16 As regulations are evolving around the world, requirements for auditable information of models and training data may increase. Commercial models may be able to provide certifications, saving companies from the effort. 17 Users want models to be open source because open means more information and more options, but what's in it for model developers? Many companies have sprung up to capitalize on open source models by providing inference and fine-tuning services. It's not a bad thing. Many people need these services to leverage open source models. But, from model developers' perspective, why invest millions, if not billions, into building models just for others to make money? It might be argued that Meta supports open source models only to keep their competitors, Google, Microsoft/OpenAI, in check. Both Mistral and Cohere have open source models, but they also have APIs. At some point, inference services on top of Mistral and Cohere models become their competitors. There's the argument that open source is better for society, and maybe that's enough as an incentive. People who want what's good for society will continue to push for open source, and maybe there will be enough collective goodwill to help open source prevail. I certainly hope so. Sounds great in theory. In practice, it's challenging for any company to thoroughly inspect a dataset of the size typically used to train foundation models. Given the same concern, many companies opt for commercial models instead. Open source models tend to have limited legal resources compared to commercial models. If you use an open source model that infringes on copyrights, the infringed party is unlikely to go after the model developers, and more likely to go after you. However, if you use a commercial model, the contracts you sign with the model providers can potentially protect you from data lineage risks. 16 Performance. Various benchmarks have shown that the gap between open source models and proprietary models is closing. Figure 4:7 shows this gap decreasing on the MMLU benchmark over time. This trend has made many people believe that one day, there will be an open source model that performs just as well, if not better, than the strongest proprietary model. As much as I want open source models to catch up with proprietary models, I don't think the incentives are set up for it. If you have the strongest model available, would you rather open source it for other people to capitalize on it, or would you try to capitalize on it yourself? 17 It's a common practice for companies to keep their strongest models behind APIs and open source their weaker models. 186, Chapter 4, Evaluate AI Systems. Figure 4:7. The gap between open source models and proprietary models is decreasing on the MMLU benchmark. Image by Maxime Lebon. For this reason, it's likely that the strongest open source model will lag behind the strongest proprietary models for the foreseeable future. However, for many use cases that don't need the strongest models, open source models might be sufficient. Another reason that might cause open source models to lag behind is that open source developers don't receive feedback from users to improve their models, the way commercial models do. Once a model is open-sourced, model developers have no idea how the model is being used, and how well the model works in the wild. Functionality. Many functionalities are needed around a model to make it work for a use case. Here are some examples of these functionalities: scalability, making sure the inference service can support your application's traffic while maintaining the desirable latency and cost. Function calling, giving the model the ability to use external tools, which is essential for RAG and agentic use cases, as discussed in Chapter 6. Structured outputs, such as asking models to generate outputs in JSON format. Output guardrails, mitigating risks in the generated responses, such as making sure the responses aren't racist or sexist. Model selection, 187. 18. The companies that get hit the most by API costs are probably not the biggest companies. The biggest companies might be important enough to service providers to negotiate favorable terms. Many of these functionalities are challenging and time-consuming to implement, which makes many companies turn to API providers that provide the functionalities they want out of the box. The downside of using a model API is that you're restricted to the functionalities that the API provides. A functionality that many use cases need is log probes, which are very useful for classification tasks, evaluation, and interpretability. However, commercial model providers might be hesitant to expose log probes for fear of others using log probes to replicate their models. In fact, many model APIs don't expose log probes or expose only limited log probes. You can also only fine-tune a commercial model if the model provider lets you. Imagine that you've maxed out a model's performance with prompting and want to fine-tune that model. If this model is proprietary and the model provider doesn't have a fine-tuning API, you won't be able to do it. However, if it's an open-source model, you can find a service that offers fine-tuning on that model, or you can fine-tune it yourself. Keep in mind that there are multiple types of fine-tuning, such as partial fine-tuning and full fine-tuning, as discussed in Chapter 7. A commercial model provider might support only some types of fine-tuning, not all. API cost versus engineering cost. Model APIs charge per usage, which means that they can get prohibitively expensive with heavy usage. At a certain scale, a company that is bleeding its resources using APIs might consider hosting their own models. 18. However, hosting a model yourself requires non-trivial time, talent, and engineering effort. You'll need to optimize the model, scale and maintain the inference service as needed, and provide guardrails around your model. APIs are expensive, but engineering can be even more so. On the other hand, using another API means that you'll have to depend on their SLA, service level agreement. If these APIs aren't reliable, which is often the case with early startups, you'll have to spend your engineering effort on guardrails around that. In general, you want a model that is easy to use and manipulate. Typically, proprietary models are easier to get started with and scale, but open models might be easier to manipulate as their components are more accessible. Regardless of whether you go with open or proprietary models, you want this model to follow a standard API, which makes it easier to swap models. Many model developers try to make their models mimic the API of the most popular models. As of this writing, many API providers mimic OpenAI's API. 188, Chapter 4, Evaluate AI Systems. 19. This is similar to the philosophy in software infrastructure to always use the most popular tools that have been extensively tested by the community. You might also prefer models with good community support. The more capabilities a model has, the more quirks it has. A model with a large community of users means that any issue you encounter may already have been experienced by others, who might have shared solutions online. 19. Control, access, and transparency. A 2024 study by A16Z shows two key reasons that enterprises care about open source models are control and customizability, as shown in Figure 4.8. Figure 4.8. Why enterprises care about open source models. Image from the 2024 study by A16Z. If your business depends on a model, it's understandable that you would want some control over it, and API providers might not always give you the level of control you want. When using a service provided by someone else, you're subject to their terms and conditions, and their rate limits. You can access only what's made available to you by this provider, and thus might not be able to tweak the model as needed. To protect their users and themselves from potential lawsuits, model providers use safety guardrails such as blocking requests to tell racist jokes or generate photos of real people. Proprietary models are more likely to err on the side of over-censoring. These safety guardrails are good for the vast majority of use cases but can be a limit factor for certain use cases. For example, if your application requires generating real faces, e.g., to aid in the production of a music video, a model that refuses to generate real faces won't work. A company I advise, Convai, builds 3D AI characters that can interact in 3D environments, including picking up objects. When working with commercial models, they ran into an issue where the models kept responding, as in Model Selection 189. AI model, I don't have physical abilities. Convai ended up fine-tuning open source models. There's also the risk of losing access to a commercial model, which can be painful if you've built your system around it. You can't freeze a commercial model the way you can with open source models. Historically, commercial models lack transparency in model changes, versions, and roadmaps. Models are frequently updated, but not all changes are announced in advance or even announced at all. Your prompts might stop working as expected and you have no idea. Unpredictable changes also make commercial models unusable for strictly regulated applications. However, I suspect that this historical lack of transparency in model changes might just be an unintentional side effect of a fast-growing industry. I hope that this will change as the industry matures. A less common situation that unfortunately exists is that a model provider can stop supporting your use case, your industry, or your country can ban your model provider, as Italy briefly banned OpenAI in 2023. A model provider can also go out of business altogether. On-device deployment. If you want to run a model on-device, third-party APIs are out of the question. In many use cases, running a model locally is desirable. It could be because your use case targets an area without reliable internet access. It could be for privacy reasons, such as when you want to give an AI assistant access to all your data, but don't want your data to leave your device. Table 4.4 summarizes the pros and cons of using model APIs and self-hosting models. Table 4.4. Pros and cons of using model APIs and self-hosting models, cons in italics. Using model APIs self-hosting models data have to send your data to model providers, which means your team can accidentally leak confidential info. Don't have to send your data externally. Fewer checks and balances for data lineage/training data copyright performance. Best performing model will likely be closed source. The best open source models will likely be a bit behind commercial models. Functionality more likely to support scaling, function calling, structured outputs less likely to expose log probs. No/limited support for function calling and structured outputs can access log probs and intermediate outputs, which are helpful for classification tasks, evaluation, and interpretability. Cost API cost talent, time, engineering effort to optimize, host, maintain, can be mitigated by using model hosting services. Fine-tuning can only fine-tune models that model providers let you. Can fine-tune, quantize, and optimize models, if their licenses allow, but it can be hard to do so. 190 Chapter 4, Evaluate AI Systems. Using model APIs. Self-hosting models control, access, and transparency rate limits risk of losing access to the model. Lack of transparency in model changes and versioning. Easier to inspect changes in open source models. You can freeze a model to maintain its access, but you're responsible for building and maintaining model APIs. Edge use cases can't run on device without internet access. Can run on device, but again, Might be hard to do, so the pros and cons of each approach hopefully can help you decide whether to use a commercial API or to host a model yourself. This decision should significantly narrow your options. Next, you can further refine your selection using publicly available model performance data. Navigate public benchmarks. There are thousands of benchmarks designed to evaluate a model's different capabilities. Google's Big Bench 2022 alone has 214 benchmarks. The number of benchmarks rapidly grows to match the rapidly growing number of AI use cases. In addition, as AI models improve, old benchmarks saturate, necessitating the introduction of new benchmarks. A tool that helps you evaluate a model on multiple benchmarks is an evaluation harness. As of this writing, Eleutherai's LM evaluation harness supports over 400 benchmarks. OpenAI's evals lets you run any of the approximately 500 existing benchmarks and register new benchmarks to evaluate OpenAI models. Their benchmarks evaluate a wide range of capabilities, from doing math and solving puzzles to identifying ASCII art that represents words. Benchmark selection and aggregation. Benchmark results help you identify promising models for your use cases. Aggregate ing benchmark results to rank models gives you a leaderboard. There are two case tie-ins to consider: what benchmarks to include in your leaderboard. How to aggregate these benchmark results to rank models. Given so many benchmarks out there, it's impossible to look at them all, let alone aggregate their results to decide which model is the best. Imagine that you're considering two models, A and B, for code generation. If Model A performs better than Model B on a coding benchmark but worse on a toxicity benchmark, which model would you choose? Similarly, which model would you choose if one model performs better in one coding benchmark but worse in another coding benchmark? Model selection 191. For inspiration on how to create your own leaderboard from public benchmarks, it's useful to look into how public leaderboards do so. Public leaderboards. Many public leaderboards rank models based on their aggregated performance on a subset of benchmarks. These leaderboards are immensely helpful but far from being comprehensive. First, due to the compute constraint, evaluating a model on a benchmark requires compute. Most leaderboards can incorporate only a small number of benchmarks. Some leaderboards might exclude an important but expensive benchmark. For example, HELM, Holistic Evaluation of Language Models, Light left out an information retrieval benchmark, MS Marco, Microsoft Machine Reading Comprehension, because it's expensive to run. Hugging Face opted out of Human Eval due to its large compute requirements. You need to generate a lot of completions. When Hugging Face first launched OpenLLM Leaderboard in 2023, it consisted of 4 benchmarks. By the end of that year, they extended it to 6 benchmarks. A small set of benchmarks is not nearly enough to represent the vast capabilities and different failure modes of foundation models. Additionally, while leaderboard developers are generally thoughtful about how they select benchmarks, their decision-making process isn't always clear to users. Different leaderboards often end up with different benchmarks, making it hard to compare and interpret their rankings. For example, in late 2023, Hugging Face updated their OpenLLM leaderboard to use the average of 6 different benchmarks to rank models. 1. ArcC, Clark et al., 2018, measuring the ability to solve complex, grade school-level science questions. 2. MMLU, Hendricks et al., 2020, measuring knowledge and reasoning capabilities in 57 subjects, including elementary mathematics, U.S. history, computer science, and law. 3. Helliswag, Zellers et al., 2019, measuring the ability to predict the completion of a sentence or a scene in a story or video. The goal is to test common sense and understanding of everyday activities. 4. Truthful QA, Lin et al., 2021, measuring the ability to generate responses that are not only accurate but also truthful and non-misleading, focusing on a model's understanding of facts. 5. Winogrande, Sakaguchi et al., 2019, measuring the ability to solve challenging pronoun resolution problems that are designed to be difficult for language models, requiring sophisticated common-sense reasoning. 192, Chapter 4, Evaluate AI Systems. 20 When I posted a question on Hugging Face's Discord about why they chose certain benchmarks, Louis Tunstall responded that they were guided by the benchmarks that the then popular models used. Thanks to the Hugging Face team for being so wonderfully responsive and for their great contributions to the community. GSM-8K, Grade School Math, OpenAI, 2021 measuring the ability to solve a diverse set of math problems typically encountered in grade school curricula. At around the same time, Stanford's Helm leaderboard used 10 benchmarks, only 2 of which, MMLU and GSM-8K, were in the Hugging Face leaderboard. The other 8 benchmarks are, a benchmark for competitive math, 1 each for legal, legal bench, medical, MedQA, and translation, Walmart 2014, 2 for reading comprehension, answering questions based on a book or a long story, narrative QA and open book QA, 2 for general question answering, natural questions under 2 settings, with and without Wikipedia pages in the input. Hugging Face explained they chose these benchmarks because they test a variety of reasoning in general knowledge across a wide variety of fields. 20 The Helm website explained that their benchmark list was inspired by the simplicity of the Hugging Face's leaderboard but with a broader set of scenarios. Public leaderboards, in general, try to balance coverage and the number of benchmarks. They try to pick a small set of benchmarks that cover a wide range of capabilities, typically including reasoning, factual consistency, and domain-specific capabilities such as math and science. At a high level, this makes sense. However, there's no clarity on what coverage means or why it stops at 6 or 10 benchmarks. For example, why are medical and legal tasks included in Helm Lite but not general science? Why does Helm Lite have 2 math tests but no coding? Why does neither have tests for summarization, tool use, toxicity detection, image search, etc.? These questions aren't meant to criticize these public leaderboards but to highlight the challenge of selecting benchmarks to rank models. If leaderboard developers can't explain their benchmark selection processes, it might be because it's really hard to do so. Model Selection 193. 21 I'm really glad to report that while I was writing this book, leaderboards have become much more transparent about their benchmark selection and aggregation process. When launching their new leaderboard, Hugging Face shared a great analysis of the benchmarks correlation, 2024. 22 It's both really cool and intimidating to see that in just a couple of years, benchmarks had to change from grade-level questions to graduate-level questions. 23 In gaming, there's the concept of a never-ending game where new levels can be procedurally generated as players master all the existing levels. It'd be really cool to design a never-ending benchmark where more challenging ING problems are procedurally generated as models level up. An important aspect of benchmark selection that is often overlooked is benchmark correlation. It is important because if 2 benchmarks are perfectly correlated, you don't want both of them. Strongly correlated benchmarks can exaggerate biases. 21 While I was writing this book, many benchmarks became saturated or close to being saturated. In June 2024, less than a year after their leaderboard's last revamp, Hugging Face updated their leaderboard again with an entirely new set of benchmarks that are more challenging and focus on more practical capabilities. For example, GSM-8K was replaced by Math LVL5, which consists of the most challenging questions from the competitive math benchmark Math. MMLU was replaced by MMLU Pro, Wang et al., 2024. They also included the following benchmarks: GPQA, Rain et al., 2023 a graduate-level Q&A benchmark 22 MUSR, Sprague et al. 2023 a chain of thought, multi-step reasoning benchmark BBH, Big Bench Hard, Srivastava et al., 2023 another REA Soning benchmark IF Eval, Zhou et al., 2023 an instruction following benchmark I have no doubt that these benchmarks will soon become saturated. However, discussing specific benchmarks, even if outdated, can still be useful as examples to evaluate and interpret benchmarks. 23 Table 4:5 shows the Pearson correlation scores among the 6 benchmarks used on Hugging Face's leaderboard, computed in January 2024 by Balash Galambosi. The 3 benchmarks Wino Grande, MMLU, and ARC-C are strongly correlated, which makes sense since they all test reasoning capabilities. truthful QA is only moderately correlated to other benchmarks, suggesting that improving a model's reasoning and math capabilities doesn't always improve its truthfulness. 194, Chapter 4, Evaluate AI Systems. Table 4, 5. The correlation between the 6 benchmarks used on Hugging Face's leaderboard, computed